Hello, this is Dr. Armon again, back by popular demand. I had a few emails asking about how to, I guess, go about answering the questions involving IR spectrum for Experiment 8 post-lab questions. So I did just a quick kind of video showing you how to interpret IR spectrum. Very simple. We're doing very simple systems here. We're just trying to compare a known IR spectrum to that of an unknown and see if it's that compound or not, similar to a melting point. You take a melting point of a compound and you compare it to your unknown compound's melting point. Are they the same? Yes, that's a good indication you have your compound. So we're going to do the same thing with IR spectra. We're going to take for example, if you were in lab, you would take the IR spectrum of your unknown compound and compare it to known compounds and try to elucidate whether or not you have that compound or not. And the compounds we're working on are amines. Amides are similar, but a little bit different. But we're just focusing on very simple amines. So it has that nitrogen, and depending on what type of substituted amine it is, it could have 1 or 2 hydrogens on it. So on that note, sit back, relax, and let's get started. Just to kind of give you a background on IR spectrometry, and it's a very powerful tool used in chemistry to help determine what types of bonds are present in a compound. So what you would do is you would synthesize a new compound and then take it to an IR spectrometer and determine the IR spectrum, and then kind to assign types of bonds based on the spectrum. Now, a molecule has many different types of energy, and we touched on this back in experiment 7, but there are 3 types of energy of a molecule. There's the electronic energy. So when an electron goes from one energy level to another, it gives off a certain amount of energy. And electronic energy we use when we're talking about UV visible spectrometry. And that's actually what you're doing in experiment 9 and 10. You're doing UV visible spectrometry, so you're using the electronic energy of a molecule. Now, vibrational energy is what we look at with IR. So bonds give off certain vibrations which are detected using infrared spectrometry. So we're looking at the infrared energy with those bonds vibration, and this is what IR spectrometry is. It's the vibrational energy. Rotational energy, if you continue in chemistry, when you talk about different types of spectroscopic tools, there's another type that uses rotational energy as well. Well, these are the 3 energies that make up a molecule. So in IR spectroscopy, we're interested in the absorption of IR radiation. And so again, these bonds vibrate. As they vibrate, they absorb infrared radiation, and we get an absorption peak, similar to what you see in a UV-vis spectroscopy. And based on the makeup of the molecule, you'll get different absorption peaks. And so another way when you look at IR spectroscopy is we call it vibrational spectroscopy, because the molecules vibrate, the bonds in molecules vibrate within it. So there are different types of ways these molecules can vibrate, or bonds can vibrate actually. And again, this is good to help elucidate the functional groups. So in lab, what you would have done is you would have taken your compound, run the IR spectrum, and then compare it to known acetaminophen, for example, IR spectrum, and look at the peaks to see if the peaks on your unknown compound matches your known compound. And so there are many different ways that you can vibrate a bond. 2 main categories. We have stretching. So atoms in a bond stretch, and they can stretch together, which is symmetric bonding. So these 2 blue atoms both stretch out at the same time. That's one type of stretching. And that's called symmetric stretching. Now, the terms aren't that important. You should just remember that there's two broad categories, stretching and bending. Now, we also have asymmetric stretching. So asymmetric stretching is when the blue atoms are the same, say these are hydrogen. If these are both hydrogen here, we can have symmetric and asymmetric stretching. So that means when one's going out, the other is coming in. Whereas in symmetric stretching, they're both going out at the same time. So when you have two hydrogens attached to the nitrogen, you can have symmetric and asymmetric stretching. So remember that, that's very important. And we'll show how all this represents in the amines over here to the right in a second. And then we have bending, and there's many different types of bending. So you have three atoms, they can bend in a certain way, and there are in-plane bending vibrations such as scissoring, rocking, so that's within the plane of the molecule. And then we have out-of-plane vibrations, which are wagging and twisting. And remember wagging, because you're going to hear that coming up. So now let's look at, what's it called? Let's look at, in the case for amines. So here we have a primary amine, a secondary amine, and a tertiary amine. So very simply, we can look for a primary amine. So this nitrogen-hydrogen bond can stretch, and this nitrogen-hydrogen bond can stretch. So they can either both stretch together, which is symmetric stretching. So you can have symmetric NH stretching. It's still stretching, right? Because again, these two hydrogens can both stretch together. Or, since there's two of the same atoms, you can have asymmetric stretching as well. So when one's stretching out, the other one's coming in. Kind of like those, you have these three hanging metal spheres. You take one, it comes in, hits it. As it's coming in, the other one's going out, and they kind of tic-tac back and forth. And so when one is going out, when one bond is stretching and the other one is compressing, you can say like a spring, then that's called asymmetric NH stretching. Oops, spelled stretching wrong again. So that's another type that can stretch as well. Again, these are very simple very simple very simple fundamental compounds. Again, when you go to organic chemistry, it gets a lot more complicated. This is just trying to introduce you to the concept. So this is somewhere there when you hear it again. So another thing we can stretch. So we talked about the NH stretching, but for amines, remember that this R group is actually a carbon, with some kind of carbon compound. And so what we can have is, we can have the stretching of this bond. And so in an amine, we have CN stretching. Now it can't be symmetric or asymmetric because we only have one nitrogen carbon bond. These are just the main, I'm just talking about the main types of stretching and bending. There's other ones as well, but these are the main ones that you are very, I guess you could say, prominent in. So those are the three main, I guess, what's the word? Fundamental stretchings you can have in an amine. Another thing you can have is you can have what's called NH wagging. So what happens is this whole, So if we look at these three atoms here, they can bend. The whole, I guess those three bonds can bend out of plane. You gotta remember this is not three-dimensional, but it looks something like this. So they have this where this NH bending can occur. Now there's other types of bendings, but this is one of the, I guess, principal ones of an amine. And it's a primary amine because this NH can bend. So we could have NH bending. That's because we have the same hydrogen, so it's the same kind of motif. So these NHs are these H's are bending out of the plane. So now let's go to secondary amines. Secondary amines, again, we have an NH bond, so we can have stretching along the NH bond. So we can have NH stretching, but there's not two different types. There's only one type. It's just called NH stretching. Because we only have one, then we can only have one type of stretching. Now with the other one, this depends. So if these R groups are the same, then you can have, remember these R's are carbons here. Let's just, for illustration purposes, both these R groups are the same. So we'll say R1 is the same as R2. And so for that, we can have symmetric CN stretching. They're both pulling out at the same time. Or we can have asymmetric CN stretching. So one coming in, the other one going out. So notice how the different types of stretching are occurring depending on what type of amine stretching, not stretching. All right. And then we can have some NH bending. This one's a little bit different because now we only have one hydrogen. So you can get, for example, these three bonds here can wag or bend. So you may get some NH bending. And yes, for secondary amines, you can get CN bending, but again, bending is happens at very low, what we call wave numbers. So we don't really look at bending that much. It's mainly the stretching. Now for tertiary amines, imagine if we say R1 and R2 and R3 are all the same. So R1 equals R2 equals R3. So it's all the same R groups, and they're carbons. So notice in that one, we don't have any NH stretching in tertiary amines. So we can have symmetric stretching. They all stretched out at the same time. So mainly what we're having is symmetric CN stretching. And we can have asymmetric. And again, since they're all three the same, you would have a very complex type of stretching. But the main thing is you can have, asymmetric, symmetric CN stretching. The main thing to note is for primary amines, as you're going to see on the IR, it's going to have two peaks for symmetric and asymmetric stretching. For secondary amine in the same region, it's going to have one peak for NH stretching. And for tertiary in the same region, it's going to have three peaks or zero peaks in that NH region. And so from that, you're going to compare that to the IR I've given you of the unknown compound and see which one of those spectrums best fits the unknown compound. So for simple primary amines, we're talking about very simple systems here, nothing too complex. We have a few unique peaks. So again, this 3400, 3300 is the symmetrical, asymmetrical NH stretching. Which one comes first or second, I'm not sure, but both of those are the result of the symmetrical, asymmetrical NH system. So we'll label that as 1. So we'll put 1 here. Then you see between 2700 and 1700, there's no peaks in this region for simple amines that we're dealing with. Now we have another peak at around 1600. This is a type of NH bending, so that's number 2. And these are the main peaks. So if you have a primary amine, you should have peaks near these numbers. So for example, 1600, I would say anywhere between 1650, 1550, in that range. If you have a peak, that's going to indicate it's an NH bending if you have a primary amine. Now at 1100, we'll say that's our important peak 3. We have CN stretching. Now this is an approximation, so it could be anywhere from say 1150-ish to 1050-ish in that region. And then we have the NH wagon, which is around 750. That's our 4th important peak. So again, in the red, you shouldn't see any peaks in this region for simple primary amines. So all the primary amines that I give you in the question should not have, if it's an unknown, should not have a peak in this region. So again, for primary amines, the first important thing, does it have these two stretching frequencies? If it does, it's a primary amine. Does it have a peak around 1600? If it does, it's a primary amine. Is there a peak around 1100? Approximately, yes, and it's a primary amine. And then around 750. But again, the key is this right here for primary amine. Because you see these two stretching frequencies around 34, 3300. That's a good indication you have a primary amine. Now we'll move on to secondary amines. So secondary amines, remember, we're going to have one NH stretching. So here at around 3300, we have our one NH stretching. So that's number 1. And then around, so between 2700 and approximately 1550. Again, this is a little wiggle room, but you see there's no peaks in this region for a simple simple secondary amine. And then around 1500, we have our second major peak, which is the NH bending. And then around 1100, we have our third important peak, the CN stretching. So what you want to do is, when you're doing the question, you look at your unknown compound, you look at your unknown spectrum, and see, does it have these peaks in it? So if it has one peak at 3300, nothing between 2700 and 1550, something around 1500, something around 1150, something around 733. That's going to tell you it's going to be a secondary amine. So you need to choose which one of those is a secondary amine. And then we also have our NH wagon, which is our fourth important peak. So again, the key thing for a secondary amine, does it have this one peak around 3300? Is there an NH bending around 1500? And is there a CN stretch around 1150? And of course, you got the wagon. But again, very important, between around 2700 around 1550, you won't see any peaks. They look empty like this. And then lastly, we go to simple tertiary amines. So again, notice, remember, tertiary amines have no NHs, so there's no peak in this region. So there's no peak in this region. This is a good sign that you don't have a primary or secondary amine. So you can mark off all the primary and secondary amines in the choices. Now between 1500 and 2600 for a simple tertiary amine, you shouldn't see any peaks. If you see a peak in that region and there's nothing in this region over here, its indication is probably not an amine, it's something else. Now the only unique peak you'll see for a simple tertiary amine is the CN stretch, which is around 1200. So you see a peak around 1200, no peak around 3300. So there's no peak around 3300, nothing between 2600 and 1500, and nothing at 750. Then it's a tertiary amine. So again, you don't have anything in the 3300 region, and between 2600 and 1500 you have nothing, and you have something at 1200. It's a good indication that you should choose the one that's a tertiary amine in your choices. Now if you see a peak between 2600 and 1500 and there's no peak at 3300, then that's a good indication that you don't have an amine, because in all these examples you've seen that this region is empty for simple amines. So if you see something in this region between 2600 and 1500 and you don't see anything at 3300, but there's a peak here, for example, that tells you it's not an amine. So let's go over that again. So what we're looking for tertiary amine, no peak in this region. No peak. Between 2600 and 1500 for tertiary amine, just like all the other amines, no peak in this region. There should only be a major peak around 1200. You should see a peak around 1200, the CN stretching. And there will be no peak around 750. There's no peak here. This doesn't count. So main thing is no peak here, no peak here. Only major peak is 1200. Now if you see a peak between 2600 and 1500, it's indication in this case it's not an amine. I wouldn't say most likely. It is not an amine. Let's take out most likely. It is not an amine or amine. So that brings today's little lesson to an end. So I hope you were able to understand what you need to do on these questions. Is I give you the three spectrum of a primary, secondary, tertiary amines IR spectrum, very simple systems. And I say these are the important peaks you should see. And then you go to your unknown spectrum, you see which spectrum it best matches with. So let's say it best matches with a primary amine. Then you would look in your choices to see which one is a primary amine. If you think, hey, this unknown spectrum doesn't match with anything, then it's not going to be anything with an NH or N in it, or NH2. So you have to look, okay, which one of my compounds doesn't have any type of nitrogen in it? And that would be that compound. So that's how you're supposed to do those questions. So I hope this lesson was informative. And if you liked the lesson or learned something new, make sure to click the like button. And so on that note, Dr. Armand signing off. Until next time.